All right, so we're starting chapter 2, section 1, and it's all about describing location in a distribution. So the first way we can describe a location is using a percentile. You guys have probably seen percentiles all over the place. As you take the SAT and the ACT and you go to college, you're given a rank, and it tells you how many people fall below you. So the higher you are, the higher percentile you are, the better off you are, because that means you're above that many other people. So to find the P percentile, you take how many observations, the percent of observations that fall less than that value. So you would count the number of observations below. The first step. So count number of observations that fall below the value. Then the second step would be to divide by the total number. And then you should always round to a whole number. You're not going to have a decimal. And you'll always round up. So let's take a look at an example. This is about Mr. Pryor's statistics class. So the first thing I want you to do with this data is draw a stem and leaf plot. So pause the video. Now that you've got your stem and leaf plot drawn, make sure you did your key. 6/7 represents a score of 67. Let's look at this problem. Jenny scored an 86. How did she perform on this test relative to her classmates? So 86, this right here is Jenny. Right there she is. My board's off again. So I would count how many fall below her. So in the first row there's 1, in the second row there's 4. So there's 1 here, 4 here, 7 in this one, and 8 in this one. So if I add them all up, I get 20. Oh, and there's one more in the next row. I get 21. So 21 students fall below Jenny. And total, there's 25. So if I do 21 divided by 25, I'm going to get Jenny's percentile. So down here, I've got all the work out. So her score was greater than 21 of the 25 observations. So it's 21 out of 25, that's 84%. Are below hers, Jenny is in the 84th percentile in the class test scores distribution. So that tells us the location of Jenny within her classmates' scores. So percentiles, that's a great way to describe the location of data. And that's just the first way. We're going to go through a couple ways. So one way we can display percentiles is in a graph called an ogive, and it's spelled ogive, but it is pronounced ogive. And this is a cumulative relative frequency graph. So as you can see, we're looking at a graph of the ages of the first 44 presidents when they were inaugurated. So there were 2 presidents from 40 to 44, 7 presidents from 45 to 49, so on and so forth, all the way down. So if we were going to find the relative frequency, that's the percentage of presidents in that category. So the first one, there are 2 out of 44, so that's 4.5%. There are 7 out of 44, that's 15.9%. And if we go through and do all of them, we could have the percentage in each category. So to get our ogive, we would need the cumulative frequency. So from 40 to 44, there's 2, and then I would add this to 7, and add that to 13, and so on and so forth. So now I know how many fall below each category. So from the 60 to the 64 range, 34 fall below it. If I was in the 50 to 54 range, 9 would fall below it. So then I could find my percentages. So 4.5%, 20.5, 50%, 77.3, until I got to 100%. And so from here, I could graph this. So from 40 to 45, I end up like this. There we go. 45 to 50 is at 20.5%, so it ends up right there. The next one, 50 to 55, is, sorry, 50 to 54 is at 50%, so this line has to connect to 50. The next line will connect to 77.3. The next one to 93.2, and then till we get to 100%. And that would be my ogive. And I can actually read information off of this graph as well. I'm going to show you that in just a second. So now that we've created this ogive, you can be asked questions about it. So the first question says, was Barack Obama, who was inaugurated at the age of 47, unusually young? So if I use my ogive, I'm going to go to 47, which is right in here. And I'm going to see where it crosses my red line. That's my ogive. It crosses, and we can approximate. I would say anywhere from 10 to 13% would be a good approximation. So the official number is 11%. We would estimate Barack Obama's inauguration age places him at the 11% cumulative relative frequency mark. President Obama was inaugurated at a younger age than 89% of all U.S. presidents. So we could say that he was unusually young. He was in the 11th percentile. So then if you were to ask to estimate the age at the 65th percentile, we would find 65 on the left side. So 65 would be somewhere right in here, and we would draw it this way until we intersect it. Once we saw where it intersects, then we would go down to find the age. And again, it's going to be an approximation. So we know it's bigger than 55, but it's not quite halfway between 55 and 60, so don't go too far when you make your estimation. So we would say about 58. So about 65% of all U.S. presidents were younger than 58 when they took age. My line is a little crooked. You can kind of see how it goes left. It should go straight down, and that's just because my smartboard is off a little bit when I drew it. So that would fall more at 58, whereas in my picture it looks about at 56, and it's not. So pause the video, take a minute, and I want you to try the check your understanding on page 89. All right, so here are your answers. The multiple choice for number 1, the answer was C. If you have questions about that, just let me know in class and we'll go over it. The second question asks you to explain what the percentiles mean. So the 87th percentile means her daughter weighs more than 87% of girls her age, and she is taller than 67% of girls her age. The third one, what percent of calls were less than 30 minutes? That was 65%, and you were reading that from the ogive. And for more than 30 minutes, that would be 35%. The fourth one, to estimate the quartiles, remember Q1, there's 25% that fall below Q1 and to the minimum. So you would look for the 25th percentile. So that's 14 minutes. And if you got close, if you said 15 or 13, if you were right there, it's still correct. For Q3, it's at the 75th percentile. So that's 32 minutes. Again, as long as you were pretty close. And then you subtract them to get the IQR, which is 18 minutes. So the next thing that describes position is called a z-score. And another term we use for this is the standardized value. So we're trying to see how many standard deviations above the mean or below the mean a value falls. So to calculate the z-score, we take x and we subtract the mean, and then we divide by the standard deviation. So take a look at this data. This is the same from before. We already did our stem and leaf plot. It says if Jenny scored an 86, what is her standardized score? So before we even can calculate that, we need to calculate the mean and standard deviation. So pause the video and calculate mean and standard deviation for this data. So you should have gotten the mean as 80 and the standard deviation as 6.07. So to calculate the z-score, we're going to take Jenny's score, which is 86, subtract 80, and divide by 6.07. And you should have gotten 0.99. So what that means is Jenny's score is about 1 standard deviation above the mean. The z-score tells us how many standard deviations. So she's about 1 standard deviation above the mean. So we can use z-scores to compare the position of individuals from different distributions. So if Jenny scored an 86 on her stats test, but she scored an 82 on her chemistry test, which one did she do better in? The mean and standard deviation for chemistry were 76 and 4. So I can't just compare 86 to 82. I got to standardize both values. So we actually already calculated the standardized score for stats. Let's go ahead and do it for chemistry. So we would take and subtract 82 minus the mean for chemistry, which is 76, and divide by the standard deviation of 4. So her chemistry standardized score was 1.5. So even though her score in chemistry was lower, she did better compared to statistics, compared to the rest of her class. She was 1.5 standard deviations above the mean in chemistry, while she was only about 1 standard deviation above the mean in stats. So take a minute and try to check your understanding on page 91. All right, so the first one, you can see the work that I did, 65 minus 67 over 4.29. I got negative 0.466. When your z-score is negative, it means the value falls below the mean. So Lynette's height is about 0.47 standard deviations below the mean height of the class. For number 2, we calculated Brent's z-score as 1.63. Therefore, Brent's height is about 1.63 standard deviations above the mean height of the class. And then the last one, it actually gave you the z-score and asked you to calculate standard deviation. So you would just plug in what you know and solve for what you don't. So you can see how I set it up there. And when we solve for standard deviation, we get 2.35 inches. So the last thing I want to talk about is transforming data. So if you did everything, if you added a number to all of your data, how would that change the measures of center, spread, location, shape, and all of that? So adding a number to all the data observations would add that same number to center and location. So that would be your mean, median, quartiles, and percentiles. However, it would not change the shape or the spread. So range, IQR, standard deviation, and the shape would stay the same. So take a minute and read pages 92 to 93. It gives a great example of this and shows you how it goes through it. Now that you've read through it, this is the data that you looked at, and so I just want you to take a look. Notice the standard deviation stayed the same, the IQR stayed the same, the range is the same. However, all the other values, the mean and the 5-number summary, they all decreased by 13. Now when you multiply by a number, if you take each observation and multiply or divide by a number, it is going to change everything except for the shape. It'll change the center and the location, and it will also change the spread. So now read it's kind of the same example, but it's continued on, and it's on 94 and 95. So here's the data for that, and as you can see, the shape, even though it's more spread out, it's still about the same. You've got the higher portion over here with a long tail to the right, higher portion here, long tail to the right. So it's still skewed right. But if you look at all of your data, it's all going to be multiplied by the 3.2 number. I don't remember. I think it was 3.28. All of those values do change. So take a minute and do the check your understanding on page 97 and 98. So number one, the shape's not going to change, but the center and spread will be multiplied by 2.54. And number two, the shape and spread won't change, but the center will have 6 added to it. And in number three, the shape won't change, but the mean will equal 0 and the standard deviation will be 1. So the last thing I'm going to leave you with is this definition of what a density curve is. I'm not going to really talk about that now. We'll do that more in class. But take a minute to write this down in your notes, and we'll cover more of that together.